Hi, welcome back. Today we are going to take a look at this avionic unit. This thing is a CDU, a control display unit, manufactured by Racal Avionics, made in England. There is a ground connection. On the front there is a CRT and a keypad. The challenge will be to get it work. So for that I will need to do the reverse engineering of the hardware, and probably I will need to do a partial reverse engineering of the code. We will see. Okay, so let's start by removing this panel here. Okay, so here we have a power supply board. Okay, so we have two nice capacitors, probably high temperature type. Okay, we can see here the flyback transformer for the high voltage for the CRT. There is a new metal shield here. We can see the yoke. And here we have the board for the CRT itself. This thing has received a shock here on that corner. Okay, so this is the keypad assembly. And we can see the front of the CRT. Okay, so we can see we have three boards. One is dedicated for the CRT. We have the high voltage power supply for the acceleration, focus, and so on. And we have also the deflection circuit. Okay, so this is the power supply board. So this part is the supervisory circuit. There is here N-channel MOSFET IRF 53 something. This part is a 555. And underneath this board there is a DC-DC converter. It is difficult to disassemble because you can see the DC-DC converter is linked to that board using several wires here. So it is difficult to see the markings of this DC-DC converter, but we can see that we have here an output voltage of minus 12 volts, and there is also a plus 12 and a plus 5 volts. It is difficult to see, but so the input voltage is here. The minimum input voltage is 19 volts and maximum 35 volts. The maximum power is 25 watts. Okay, so I will do the reverse engineering of this little board also. So I started by the reverse engineering of the power supply. It uses the DC-DC converter from Airy Power. I found the datasheet of that unit. You can see inside it's very nice. It's a hybrid circuit, and you can see several resistors here on the ceramic substrate. There is also a block schematic of this power supply. There are two circuits, the power supply itself here and a supervisory circuit on the bottom here. The 28 volts input is here. There is here a protective diode, and there is here a MOSFET. Okay, so we will see in one moment what is the goal of this MOSFET. And the DC-DC converter is here. The input voltage range is 19 to 33 volts exactly. So there are three outputs, plus and minus 12 and plus 5 volts. So we can see that we have a small power supply using this multi-vibrator and this voltage doubler. This is the grid command for this high side MOSFET. Okay, because in order to have a conduction of this MOSFET, we need a voltage on the grid here, which is above the power supply. So this is the goal, okay, of this capacitor, these two diodes here, and this capacitor. So we can see that at startup, we have this resistor and this diode, which permits to turn on this MOSFET. When the power supply is activated, the grid voltage is above the source voltage, therefore this diode is off. There is one important part on that system, which is this diode here of 33 volts. So actually this is the voltage limiter. Another interesting signal is this line here. So this line is actually a remote control of the DC-DC converter. So if this input is connected to ground, this inhibits the DC-DC converter. So this line is connected to this mystery part. Okay, so one line is connected to ground, the second line is connected here So we can see that we have actually a micro switch which is inserted on this plastic stuff here. Okay, so my guess is that we have here a tilt switch. So I think that this permits to detect a shock. If a shock occurs, there is probably a short circuit inside here, so we should find maybe a mass inside. And in that case, there is a short circuit between these two lines, and the power supply is disabled. Yes, okay, so this is maybe the reference of this part. Okay, so bingo, we have a micro switch, and here we have something which seems to be a simple mass. Yeah, and there is a spring. Okay, so for a given acceleration, there will be a displacement of the mass, and this permits to adjust the trip point of the acceleration by changing the position here of the mass. We have here the CRT assembly, okay, and we can see the deflection coils. So we have a pair of deflection coils here, and another one here. You can see color is different. So this is a high voltage flat back transformer, and we have here the CRT board. It is possible to disconnect everything. Okay, so we have here the switching transistor BU407. There are several gas arrestors, one here, two here, and a fourth one here. So here there is another transistor, BFY50. Here we have a dual monostable, and here a dual op-amp, a classic TL082. Here we have an MJE3055 power NPN transistor. During the reverse engineering, I noticed some soldering issues. For example, concerning this resistor here, R41, which is an RB59 type or something like that. So we can see here the very bad soldering, and actually there is no contact here. So this pin is isolated from this track. And there is also this pin here. It is probably due to the heating of the resistor. Maybe the diameter also of this pad is too small, considering the heat and the diameter of this pin. So we can see also other problems here. So this unit was defective, so I will resolder everything. This is the power supply and the video circuit of the CRT. We can see the CRT on the top here. The filament is here. It is supplied with a DC voltage of minus 12 volts. So I think it is connected to the minus 12 volts in order to balance the power supply currents between minus 12 and plus 12 volts. And the cathode is here. It is connected to this amplifier, which is a video amplifier. Okay, it uses this high frequency transistor BSX20. This stage is supplied with a positive voltage, probably between plus 50 and plus 100 volts. It is a very simple circuit. The input is here. It is connected to this trimmer. This trimmer is connected to the video processor board. There is here a common collector stage, and we have video signal here on the input. So this trimmer permits probably to optimize the contrast. Here we have the power supply for the acceleration anode. This acceleration voltage is adjustable using this trimmer. This power supply should be between 1000 and 2000 volts. There is a second adjustment here for the focus, which is here. The pinout of the CRT is here. The last circuit concerns the grid or VNELT, which is here which should be negative relative to the cathode. The grid is connected to the output of this amplifier. So we can see that there is a gain of 11 regarding the input here. So if you consider that V0 is 0, so you have a non-inverting amplifier, okay, and the gain is 1 plus the ratio of these two resistors, that is to say 11. And if you consider that Vin is 0, in that case we have an inverting amplifier and the gain is the ratio of these two resistors, that is to say minus 10. Okay, so without calculation, using the superposition theorem, we can calculate the output voltage here, the grid voltage, according to the input voltage here, and this offset voltage V0. The input voltage of this amplifier is connected to a DAC circuit, which is on the processor board. Okay, it uses an amplifier with a gain of 2 and a classic DAC at ZN428. This part was intensively used by Elector magazine 30 years ago, so I think I bought one or two in Paris when I was young. So this DAC permits to adjust the luminosity by firmware. The next circuit concerns the vertical deflection. The Y deflection coil is here on the right, so I have measured the inductance of this coil. Okay, the inductance is approximately 60 millihenries. Okay, we can see here this power transistor MJE3055. So this is the voltage to current converter. You can see these two current sense resistors here. There is a diode which permits to compensate the base emitter junction here with temperature. Okay, so we can see that this transistor is biased using this shock inductor, which has an inductance of 240 millihenries. This inductor permits to have a high bias current here, and it permits also to have a small AC current. Approximately 80% of the current flows through the deflection coil, and 20% of the sawtooth current here flows through this shock inductor here. There is of course a capacitor which permits to have a bidirectional current flowing through the deflection coil. The shock inductor is that device here. The rest of the circuit is the sawtooth generator. So we can see here the integrating capacitor. Okay, so there is more or less a constant current flowing through this capacitor. So therefore there is a linear sawtooth here. The ramp is fed to this voltage follower, which is the Motorola PNP Darlington MPSA 64. So the sawtooth appears on the emitter here and is fed to the voltage to current converter. So we can see that it is not a perfect current source, but it uses this resistor, which is a kind of bootstrap technique. So therefore, across these two resistors here, there is a constant voltage corresponding to the voltage between the emitter here and the base, that is to say approximately 1.5 volt. But it is not perfectly constant. There is another resistor here connected between the output and the middle point of these two capacitors. So I guess that this permits to correct the nonlinearity associated with this circuit here, but I am not totally sure. And finally there is this SCR which permits to discharge these two capacitors. The discharge is provided by the horizontal trigger signal, which is here. The vertical frequency is approximately 65 Hz, and there is here a pulse of 300 microseconds for the synchronization. So this corresponds also to the vertical backtrace. The last circuit concerns the X deflection. The X deflection coil is on the right here. Anyway, we have the switching transistor, okay, which is driven by a pulse transformer. The pulse transformer is driven using this transistor, okay, which is driven by this monostable. The input of that circuit is a horizontal trigger signal. The period here is 64 microseconds. So therefore, there is a classic horizontal frequency of 15.625 kHz. The duration of the pulse is 2.66 microseconds. This pulse corresponds also to the horizontal backtrace. So here we have the flyback transformer. When this transistor is on, there is a discharge of this capacitor. through the deflection coil. So there is a linear increase of the current here. This inductor permits to adjust the horizontal width of the image. It is this big inductor here. And the pulse transformer is here. The flyback transformer here delivers the different voltages. One is used for the cathode circuit we have seen, probably between 50 and 100 volts. And the second voltage is a high voltage for the acceleration, something between 1 and 2 kilovolts. And there is here the very high voltage for the post-acceleration of the CRT. So there is here another negative power supply which is used for the grid circuit. So this is the video processor board. There is a microprocessor here, 6802. There is this EEPROM 27C32, which contains the code. Only the address bus is used for this processor, so this permits the scan of the video memory actually. So there is here what I supposed to be a PAL at the beginning, but actually it is a PROM. It is an 82S123. And there is here another EEPROM which contains the font for this video controller. Okay, we can see that the data bus of this EEPROM is connected to this shift register parallel to serial converter. First, it can be interesting to do the reverse engineering of this little part here. Now, this is the schematic diagram of the video processor board. We have in the middle here the EEPROM, which contains the font. We can see that the data of this EEPROM is connected to this shift register, which is a parallel to serial converter. Okay, so at the output here we have the video signal. So therefore 1 byte here corresponds to 8 horizontal pixels. Here we have 7 bits for the address. So this corresponds to one particular character which is defined inside this EEPROM. And we have 4 lines here, okay, which permits to select the line. So one symbol corresponds to 16 bytes. So we have here the video memory, and here we have 7 bits corresponding to a particular character. And we have another bit here which permits to invert the video. The address bus here is connected to this multiplexer. The 10 bits A input is connected to the main processor board. Okay, we can see we have here 10 inputs. So this permits to write a particular character inside this memory. The address here corresponds to a particular position X and Y on the screen. The second input here, B, is connected to the address bus of the microprocessor. So this permits the scan of the memory and to perform the display. Now we can see we have 2 specific lines here. One permits to connect the address bus here to the input. The second one permits to write the data here to the address. It is also possible to read a particular character code from that memory. We can see that this board is seen like a peripheral regarding the main processor board. We have a data bus, a chip select, and a read-write signal. Now this is the microprocessor 6802. This guy here associated with this EEPROM, which is here. So we can see that the data bus of this microprocessor is not connected to anything. There is no input-output on that microprocessor. Only the address bus here is connected to the memory in order to perform a scan. So therefore, this processor is used as a super-duper counter. I will show you a part of the disassembly of this code. It is very strange. I did a dump of this EEPROM. So we can see the binary file on the screen. So one line corresponds to one character. So we can see that we have actually 143 different characters, but as we have seen, only 128 characters can be displayed. We can see here on this Excel sheet the same file. The first line corresponds to the working line. and this line is converted into a character here on the screen. Okay, so this one corresponds to this byte, and this one to this one here. On that column, I have replaced all zeros by a blank, and on the third column, I have replaced 1 by a square. So it is possible to copy and paste every line to the first one and to see a particular character, but I wrote a macro for that, so it is possible here to select any character. The maximum is 127, 28 because I start with 1, not 0. So this is the last character which can be displayed. And we have 16 or 15 more characters here which cannot be displayed because the MSB is used for the video invert. And this is the last one. So this is the macro which permits to copy any line to the first line, and I wrote a second macro here in order to display all characters in one page. This is this button here, and we have here all characters. We have here the complete ASCII character set plus some special symbols. This is the first test. I have connected this unit to a 28 volts power supply. Okay, so let's turn on the power supply. Okay, so we have something. We have the version of the firmware here, S302 and self-test OK. The display is quite sharp, but on the video it seems a little bit blurry. We should have 8 lines of 19 characters, I think.